Hi class. In this video we're going to look at periodic trends as well as look at some problems that have to deal with electronegativity. So let's just get started here. When we're talking about the periodic table, we're going to notice a couple different trends that start to occur here. And so the three that we're going to talk about today are the trends in radius size, ionization energy, and the electronegativity. So the first one here is the trends in radius size. So what that means is how many orbitals are starting to fill up as a result of extra protons and electrons that are being filled in as a result too. So if you look here, you're going to see some different trends that are starting to occur here. For example, in this group 1, the alkali metals, you notice as you're going down the group, they're getting larger and larger. Well, this has a lot to do with the fact that the element is getting larger and it just needs simply more orbitals to go around to fit all those electrons. Now, since there are these higher amount of electrons in the outermost shell, it gives it a larger radius size. So you'll also notice that as you're going across the periods that something else is occurring, how they're getting smaller and smaller. And this is just one more picture of it to show each element a little bit larger here. Notice one more time that the size tends to increase going down a column and the size will start to decrease going across a row. And you might wonder, well, why does this happen? Well, this happens because the number of energy levels increase as you move down the periodic table, as we had just mentioned. So whenever you're over, here at rubidium, which is in period 5, it has quite a bit of electrons going around it. So the atomic radius is larger as a result. Conversely, if you wonder what's going on as you're moving across the periodic table, you start to increase the number of protons, which makes sense because we know the periodic table is arranged by increasing atomic number. But what's happening is it's also getting more electronegative as you go across the periodic table. And so whenever you're going across, it actually pulls those electrons in tighter, so it'll reduce the size of the atom. So let's go and look at a couple elements here and see if we can order these correctly. So you can do some of these on your own if you want. We'll just do this first one here together. We'll look at rubidium, potassium, and sodium. Let's go back here to this page. So here's rubidium, and here's potassium, and here's sodium. It wants decreasing order. Okay, so we need to start with the biggest and kind of move down. So if we had to order these, we would put rubidium first, followed by potassium, and then sodium would be last because we are going to decreasing. We're starting with big and we're decreasing as we go down. Okay, so let's go on here. And you can try some of these on your own. Just use this page. You can go back on the video and just go back here and take a look and see if you can order some of them on your own. Okay. The next thing that we're going to look at is something called ionization energy. And this is one graphical depiction of the periodic table. You can look by colors here. If you look down here at this very pale yellow, that would signify low energy. And as you get up to this pinker region, it's going to be high energy. So if you look here, it's pretty high, and then it's getting to be lower energy as you go down. Whereas you're going from left to right on the periodic table, notice how the energy is actually increasing. Okay, so it takes a lot more energy to actually strip an electron away from its outermost shell. And so this kind of explains this a little bit better. It's the energy required to move an electron from an individual atom. And as we had just mentioned, it tends to decrease going down a column, and it tends to increase going across a row. So decrease going down a column, increase as we go across the row from left to right. Okay, and this is going to go hand in hand with our next section, which is electronegativity. So you might start to ask yourself why these trends happen the way they do. Well, they decrease going down a column. Why? Because electrons are further away from the nucleus at this point. So it's easier to remove those outermost electrons. If you're sitting here with, let's just do rubidium again, and it has all of these electrons that have filled out this outermost shell out here. Well, it's large. So these electrons out here, okay, so we're positively charged here in the center with rubidium, but these electrons are kind of out here alone by itself. It doesn't have that pull from this positive center. So therefore, it's pretty easy just to lose these electrons. It's no big deal, okay? But if you move across the periodic table, where our next trend is going to talk about electronegativity, well, over in this area, our nonmetals, they have an electron affinity. They like electrons. They want those electrons. So therefore, it's very easy for them to strip away from something over here like rubidium. Rubidium has these electrons in its outermost shell. It doesn't really care. It doesn't have that positive pull from the nucleus anymore. So in order to be happy and make some friends, we'll just kind of shift his electron away. They'll gladly accept it over here because they like electrons, because they are more electronegative. Okay, so that sets the stage for our next, let me just get rid of some of these little scribbles here. Okay, for our next trend, which we need to know about it, which is the electronegativity. So that is the relative ability of an atom and molecule to attract shared electrons to itself. This increases from left to right because we had just mentioned that over in this area, the nonmetals especially are very electronegative. And right here in the center, they have the ability to share electrons amongst themselves. So we talk about this later. They'll form what's called covalent bonds. Over in this area, though, they'll form more ionic bonds, and we'll talk a little bit about the differences in these two areas later on, and we can actually determine by the differences in electronegativity if it's going to form an ionic bond or if it's going to form a covalent bond or a polar bond, etc. So as a result, let's just look one more time here. The electronegativity will increase as you go from left to right, and it decreases going down. Okay, so electronegativity and the ionization energies kind of go hand in hand whenever we're dealing with trends. So why do these trends occur going from left to right? So the closer the electrons are to the center, the stronger the pull of the electrons. Why do they decrease? Well, we had just mentioned the further the electrons are to the center, the weaker the pull of the electrons. So whenever they're out there really high by themselves, out there in their outermost shells, they just do not have that positive pull from the nucleus anymore. So therefore, it's very easy for those nonmetals that are more electronegative to simply steal it. Okay. So our next topic that we're going to talk about are electron configurations. And whenever atoms are at their ground states, they're considered stable. So we're going to talk about this right here. So this is the orbital filling sequence, and we'll look at this on the periodic table in a second where all of these are located. But we start here at the 1s, okay? Now these are orbitals, S, P, D, and F. And if you recall, I think we talked about this a little bit in class, but in the s orbital, we can fit 2 electrons, okay? That's it. So we can actually get 1 electron, 2 electrons. Now you're probably noticing that I'm putting these up arrows and these down arrows, and we talk about this in a minute, but these are the spins of the electrons, okay? So they go up first, and then they come down next, and we have to fill these in one at a time, which we'll talk about in a minute also. After the 1s, we go to 2s, which again, that s orbital is sphere-shaped, and if we were to look at this on a coordinate plane, it's just this little sphere-shaped, and it would have 2 electrons that can fit. So this one is 2s, so we would be over here, we would fit 2 electrons. Okay. Now the 2p are actually dumbbell shaped. Okay, so let me get rid of this here, and we will make some dumbbell shaped orbitals. Now notice how there are 3. 1, 2, 3. Each one of these boxes can fit 2 electrons, so we can get a total of 6 here, right? So we don't really know where the electron is at any given time. and we talk about the person that kind of came up with that Heisenberg here in a minute, we can just get an indicator of where they are. It's impossible for us to determine with exactness of where the electron's going to be. We can only get an estimate. So they follow along in these dumbbell shaped here when we have what's called P of X. Now, you'll talk about this more when you get to higher levels of chemistry, but P of Y and P of Z. The only thing that you need to know here at this level is the fact that they are dumbbell shaped, that you still can only fit 2 electrons per orbital, and then all of these together would give us 6 for this P area. Okay, then moving up to the 3s, again, you can fit 2, and then you can fit 2 times 3, which is 6. 2. Now you have D. Okay, D looks a little bit more funky, and I'll show you a picture of that, I think, a little bit later. If not, they're in your tech book. But again, they can fit 2 electrons. Okay, and notice how I fill up each box one at a time first before I move in and do the downward spin. We can't just put them in together, and we'll talk about who came up with that rule in a couple minutes. But if you notice here, you can fit a total of 10 electrons in the D orbitals. Okay, so this is the orbital filling sequence, and we'll move on here and talk about whose sequence kind of came up with this, the Aufbau principle. Okay, he states that each electron occupies the lowest energy sublevel available. So we would start here with the 1s and then the 2s, the 2p. This starts to become a little bit more applicable to this Aufbau principle once we get up to the 3D and the 4S. There are different elements like copper, for example, that will go ahead and fill up the 3D, and they'll steal from the 4S to do that so that they can become more stable. They don't really, if copper has 9 out here and all it has to do is steal 1 from the 4S to make 10, it's going to do that. It's going to fill up this 3D so that it's happy and more stable and not erratic out there with 9 electrons in its outermost shell. Again, that is an advanced chemistry concept, but just know that that does indeed occur. Okay, so rules for electron configuration. The Pauli exclusion principle states that no 2 electrons in the same atom can have the same set of 4 quantum numbers. So whenever we were just sort of talking about this before, how these have like the down, you have to fill up each one before you move on to the next level here. So there's this thing that we call the triangle method, and if you wanted to write these out, you can, but this is kind of how they fill up. We have the 1s first. Whoops, my arrows are really off. 2s, and then this isn't easy with a mouse. 2p to 3s, and then 3p to 4s. Why is this so complicated? I'm going to try and get this through. Hopefully you're getting the point here. 3d, 4p, 5s. Okay, it just kind of keeps going like that. Okay, this is how they fill up, in case you're wondering why the periodic table looks the way it does, especially with the lanthanides and the actinide series. Okay, so what does this all mean? Well, let's actually take a look at this. If you look at this periodic table, there are different regions, okay? Over here in the pink side is where your s orbital lies. And then over here, this blue is the p. The one where I told you earlier that can fit up to 10 electrons, well, check it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's the d orbital. And then this f orbital, that's going to have 7 orbitals with the 2 actual electrons each. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 can fit in there. Okay, so the 6, 1, 2, 3, 4, 5, 6 can fit here, 10 and 2. Sphere shaped, dumbbell shaped, interesting shaped, sometimes little donuts. And then these get really awkward, but you don't have to worry about those at this level either. Okay, so this is going to help us with electron configurations. So let's say I wanted to know the electron configuration for beryllium. Okay, we're going to point out beryllium here. Well, so far it's filled up, it's 1s, right? And we have, this is the first period, so we have 1, and it's still an s. Hydrogen and helium go together. Okay, so we have 1s, and we filled up 2 electrons. Not done yet, because we're here at beryllium. Now we put 2 down for the second period, and we have, it's still in the S category, right? We have 1, 2. Now we can stop. So we have 2s2. This is what I call the electron's address on the periodic table. Okay, that's its electron configurations, how we can locate certain elements. So let's do another one. Let's do iron, because it's getting further down on the periodic table. Okay, so we're going to do the same thing where we're going to have 1s2. Okay, we're not done yet because we have to keep on going. And then we do 2. Okay, so we filled up 2s2, didn't find iron yet. And then we're coming over here and we filled up 2p6. Now if you go back to this little triangle that I was doing earlier, we did 2s2 and then we have 2p6. So we would expect 3s to come next. Well, let's go find out. Okay, so we filled up the 2p6, 1, 2, 3, 4, 5, 6. We're all done. Didn't find iron yet, so we're going on to 3s2. Okay. Okay. And then we're going to come over here to 3p6. Still didn't find iron. Okay. And now we are down here at 4s. Notice how the 4s2 came first. Okay. And now it goes back up to 3d. And now let's count. 1, 2, 3, 4, 5, 6, 3d6. That is iron's little address on the periodic table. So let's take this out. Let's check this out. We had 3p, we went to 4s next, and then we came down to 3d. Okay? It jumps down here. It looks a little bit strange, so you have to sort of memorize this. And then it goes as usual, 4p, 5s. So you use these two in conjunction with one another whenever you're trying to find out the electron configurations of different elements. Okay, so based on what we've learned about the arrangement of electrons in periodic table, I wanted you to be able to let me know who lives at this address. Well, there's shortcuts for doing this. So let's just go look. It ends here at 5s1. Okay, I'm going to go back and do a little shortcut here. So we said it was a 5s1. We're going to go here to 5 periods down. So 1, 2, 3, 4, 5. Okay, we're at 5. 5s1. We're at rubidium's house. Okay, that is the electron configuration. That's how we can go backwards and find these. Okay, let's do this one. 3p5. Let's go find out who lives there. Okay, so we have 3. We're in 3. Not in S. We're in P. So 1, 2, 3, 4. We're in chlorine's house. Okay, that's the electron configuration for chlorine. So hopefully this will help you a little bit as you are going along through some of the worksheets. Use this PowerPoint in conjunction with your tech book. There are a lot of little videos in there too that will also help your understanding. It may look far more sophisticated and pretty than these do. But hopefully this gives you an idea of what to do. Use these in conjunction with those other videos in your tech book, and you should be just fine whenever you go to complete your worksheets. Alrighty, we are done with this for now. Talk to you soon.